So welcome everyone. It's nice to see so many people to this new term of the one word probability seminar that started quite some time ago in bad time, I would say, but now we are in better times, but it's still nice to be connected somewhere, somehow, even if we are far away from each other. So the organizers for this term are myself and Roger Van Pesky.
Right.
Let us thank Shankar Bhamidi and David Aldous to agree to be our first speakers in this start of the new term. We will start with the talk from Shankar Bhamidi. Shankar is professor at the University of North Carolina, Chapel Hill, and he will be talking about, he will give us a user's guide to Aldous fringe convergence for random trees. And I think we can start. So please, Shankar, the floor is yours.
Okay. Thank you. I figured since there are two back-to-back talks, instead of having like a talk which is like all shock and awe and about how amazing some results are, I figured it maybe my talk I would aim it more at a pedagogical level. So in the sense that um, I'm back at Berkeley, and when I was a grad student, in fact, advised by Professor Aldous here. There were many of his papers that I read, amazingly beautiful papers. And one of the most beautiful papers was this fringe convergence of random trees. And once again, I think it's quite well known, but maybe not as well known as some of his other fundamental papers. So I figured I would use this opportunity to kind of discuss, the fundamental contribution of that specific line of work and its impact that it's having, quite for a long period of time. Um, what I'll do is that I'll start with sort of three motivating examples. Then I'll quickly tell you about the work on fringe convergence for random trees. Now, the sort of unifying thread in all the motivating examples I'll give you are something called continuous time branching processes. And so this continuous time branching processes are analogs of what we've all seen, we typically see in let's say, a basic measure theoretic probability class, like discrete time branching processes, just a little bit more complicated because you keep track of the time at which people give birth to children. But instead of telling you the general theory that these great Swedish probabilists, Jagers and Nerman, developed in the 70s and 80s, I'm just going to show you how this specific object shows up in all the three models that I'll start with. And I will use all this is fringe convergence to show you. Again, there will be not much rigor, no rigorous ideas in the talk, but more the sort of intuition behind the main results. And so once you know what the limit object should be, then it turns out, okay, one has to work a little bit hard, but you can make all of these sort of rigorous. So that's the basic plan. So sort of one slide on the philosophy of local weak convergence, and sort of maybe coincidentally, my so very close friend Remco van der Hofstad, who's sitting right next to me, he's giving a 2-hour seminar at the MSRI today on the same topic. But the general there are experts, of course, here who know all of this. But for others, maybe the one slide philosophy on what the main goal of this area is the following. So quite often we're looking at discrete structures whose size, for example, number of vertices, is going to infinity. And so most of the stuff in this, actually all of the stuff in this talk will be just a sequence of random trees on n vertices. At stage n, you have a random tree on n vertices. So as n goes to infinity, you want to understand asymptotics. And so what does it mean? We have structures whose size is becoming larger and larger. So one way to make this precise is you sample a vertex at random from this large tree and look at a local neighborhood. So fix some k, k equals 10, 20, but fixed k. And maybe for you look at a vertex at random, you look at the ball of neighborhood k around this vertex, and you want to understand, okay, what does this look like, at least for large n? And in particular, can you make sense of does this convergent distribution for each fixed k to the ball around some limiting infinite object? Okay, so this above sort of, if you can do this for model classes, then automatically this gives asymptotics for local functionals. It allows you to say, okay, degree distributions of these objects converge to degree distribution, some degree distribution on the limit object. But maybe, for me, the first extremely non-trivial sort of finding in this whole area is this implies convergence not just for local functionals, but in many settings, again, under assumptions. It implies even convergence of global functionals. So one example to keep in mind is suppose you look at the adjacency matrix of your sequence of discrete structures. You can look at the spectral distribution of the adjacency matrix. So if you have an n by n graph, you look at the adjacency matrix, you look at its eigenvalues, and you look at the empirical distribution of these eigenvalues. So you have a random probability measure. And so, but the bottom line is this depends on the whole graph. It's not just a local quantity. But once you have local weak convergence, under some minor technical assumptions, you automatically get convergence of this sort of global structure as well. Okay, and so this is sort of one of the amazing findings in the last, let's say, 20 years. And starting with the work of Aldous, things like the random assignment problem, Benjamini and Schramm on random walks on planar graphs, and all the way up to sort of the modern time with Justin Sales's work on connecting sort of random walks and curvature and cutoff. So, okay, bottom line, local weak convergence, understanding what happens at a local level is extremely powerful. So now I'm going to give you the main motivating examples. So the unifying theme is each of these are models of tree growth. All of them have the following structure. You start with one vertex, which I'm going to call the root. I'll use rho or r to denote this vertex, and connected by an edge to another vertex. And sometimes I'll call the root vertex 1. And at each stage, new vertices enter the system and they connect to an existing vertex via some probabilistic rule. And so the main change will be the probabilistic rule that will be used in the 3 examples. And here's a small typo, but we're going to think of edges directed away directed from parent to child. Okay, so as it shows over here, from the root to vertex 2, that's what you start the system with. And then the system keeps evolving via addition of new vertices that enter the system and connect to some pre-existing vertex according to some rule. So the first example is the following. So this is often called tree models with choice. So here, what we're going to do is, and I will keep the applied motivations to a minimum. One can look up all of these, but that's not the main goal of this talk. But all of these come from like relatively nice stories in applied probability. Okay, so the first model is the tree models with choice. So here, what we're going to do is fix k. Let's say k equals 2. And suppose you've constructed your network, your tree up to stage n. So now a new vertex n plus 1 enters the system. It samples k vertices uniformly at random from your graph, from your tree. And so there are 2 variants of this model. So the min model is the following. Amongst the sampled vertices, remember you sampled, let's say, 2 vertices at random, you pick the vertex with the minimum degree, breaking ties uniformly at random. And the max model is, once again, let's say you've sampled 2 vertices. Amongst your 2 vertices you've sampled, connect to the vertex with the maximum degree at that stage. Okay, and you can look at variants of these. And so what I'll tell you, or I'll give you the intuition. So this is sort of joint work with Omer Angel and Robin Pimentel towards the end of the talk. The second model is network models with delay. So here, so fix some distribution mu on the interval 0 to 1 and a parameter alpha. In fact, you can just take alpha to be 0 just to fix ideas. And take theta I, these are IID random variables with distribution mu. And so what these theta I's will tell you is, in some sense, they give you the amount of delay that vertices experience in terms of the amount of information they have when making decisions. So what do I mean by this? Once again, we're looking at random tree growth models. Once you've constructed the tree at time n, vertex n plus 1 enters the system, but it has only information of the network at time n times 1 minus theta n plus 1. So it doesn't have the information about the entire tree at that stage, but only the tree at time n times 1 minus theta n plus 1. So what this means is it only knows who are the individuals present at that time. And it also only knows the degree of vertices present at that time. I mean, their degrees at that time, not their full degree by time n. And using this information, it decides to connect to a vertex v in in the tree with probability proportional to the degree of the vertex at that time n times 1 minus theta n plus 1. And if you want to put in a parameter alpha, you can also put in a parameter alpha. So what I'll do is I'll give you intuition behind this joint work with Sayan Banerjee, Partha Dey, and Akshay Sakanaviti using this fringe convergence. And the final model is sort of motivated by social networks, more precisely something called attributed network models. So the main goal here is most social networks, so vertices have different attributes. We all think hopefully we're infinite dimensionally complex, but for the sake of this talk, let's assume each individual in the network has just one of k possible types. And the network evolves via taking into account, so it's dynamic, but it also takes into account types of different individuals and also the popularity of different individuals as time progresses. So what I'll tell you is work with Nelson Antunes, Sayan Banerjee, and Vladis Pipiris. And what people have been interested in are models of these social networks. And the reason for this is these sorts of attributed networks, or real world networks like Google, Instagram, X, and so on, they play an outsized role in how information diffuses in our modern society. And then there are a number of folk theorems that people think, things like, okay, different centrality scores behave similarly, whether you look at how popular people are based on how many friends they have, or more complicated functionals like PageRank, all of them behave similarly. And sort of one needs to understand whether, mathematically these are true. And so sort of the main model that people use to understand these sorts of things in applications is the following. So we have we have our types 1 up to k, and we're going to fix a probability measure, a probability mass function on these types. So it tells you what density of people are of type 1, type 2, up to type k. And so if you don't like k, just take k equals 2. There are two types, minority and majority. And you fix an asymmetric function, potentially asymmetric function kappa on this type space. And so what this asymmetric function measures is the propensity of pairs of nodes of different types to connect based on their attribute. And just ignore the final bullet point here, this gamma in 0, 1. Gamma is going to be 1 for this talk. And so the basic model is the following. So once again, it's a network tree growth model. Vertices enter the system. The type of a vertex, when a new vertex enters the system, its type is sampled according to this distribution pi. And now once it has its type, so the type distribution is independent of the state of the system. The type of the new individual is independent of the current state of the system. And once we have sampled the type of the vertex, now this new vertex has to decide who to connect to in the existing tree. And so the probability it connects to an existing vertex is proportional to this kappa of the type of this new vertex, which is a star, the type of the old vertex that it's thinking, okay, should I connect to this vertex or not? So kappa AV comma A star. But it also uses the degree of this present vertex to decide whether it wants to connect to or not. So it's proportional to both the propensity, the type of the vertex and its own type, and the popularity of the present individual. Okay, so these are sort of the three main models in town. So this interpretation of this kernel, it's asymmetric. The first coordinate represents the type of the old individual that's already in the system. And the second coordinate represents the type of the new individual that enters the system. And this kappa of these two objects measures the propensities of the propensity of these two types to connect. Okay, and so I'll just skim over this, but in the applied context, what people are interested in are not just things like the degree distribution of the graph, at least as the network becomes large, but they're also interested in joint distribution of attributes and types. They're also interested in more complicated functionals, for example, the PageRank scores, which is a more complicated way of measuring centrality of different individuals in the graph, and also the PageRank scores, the joint distribution between PageRank scores and types. Okay, so people are interested in lots of different quantities of these models, and much of the applied literature, they try to simulate these systems and then understand what happens, at least numerically. And so the main goal in all of these three problems that I've told you is, can one understand these models as n goes to infinity mathematically? Okay, so the main or one of the main tools now, going back to the work of Aldous in this paper, is structure theory for finite and infinite trees. So backing up a little bit, so local weak convergence that I mentioned at the beginning of the talk is now a very well-established field. But in the context of trees, it has, so I will say two things. So the first thing is, in the context of trees, it has a particularly nice and simple structure. And the second thing is, in the context of growing trees, when you're trying to prove things, this structure turns out to be extremely useful to get relatively soft proofs for complicated models. So what do I mean by this? So suppose you have a finite tree T. So you have a root R. Now, suppose you fix another vertex V. So once you've fixed a vertex V and a root R, now you can happily decompose the tree uniquely using the path from the root to this vertex V. So there's a unique path. You're looking at trees. That's the main goal of this talk. You're looking at trees. So once you have this path, you can look at all individuals whose shortest path from the root passes through this fixed vertex V, or V0. So that I'm calling this tree T0 of V. Then you can look at all the vertices whose shortest path from the root passes through the parent of V0, which I'm calling V1. This is the collection T1. And then the parent of V1, which is T2, all vertices whose shortest path goes through V2, that's T2, etc. Okay, so for tree-based objects, it's very easy to decompose. Given the root R and another vertex V, you can decompose the entire tree via these subtrees. And in particular, you can think about, okay, so if you fix a vertex V, you can just, maybe you have a tree on 1 million nodes, then maybe as a starting point, you can just focus on this much smaller tree, T0 of V. That is often called the fringe subtree hanging from this vertex V in this big tree T. Then you can say, okay, I can understand this fringe subtree. Maybe I will look at the subtree T0V and T1. I should have put a V here because it does depend on V. But I'll just look at T0V and T1V and try to understand the structure of these two subtrees. Okay, if I can understand these, I will try to understand T0V, T1V, and T2V, and so on. Okay, so for trees, things become, especially local neighborhoods, become much nicer. And so this goal that I just now told you, suppose you want to just understand T0V, T1V, T2V. This is called the fringe up to level 2, centered at this vertex V. Okay, so now let's back up. So what are the models that I told you about? We have a sequence of growing trees, tau n. So uh, uh, one can imagine that in many contexts, as the tree becomes larger and larger, the location of the root goes very far away. It's very far away from I'm sorry, so I should have said the vertex V that we're going to sample is a uniformly selected vertex. So that is going to be our V0. And now if you look at the path to the root, we can imagine that in many cases, the distance of the root from this vertex, that you randomly sampled vertex, it becomes longer, not longer and longer, but basically goes off to infinity. So suppose our goal is to understand the question, if you sample a vertex at random and you want to understand the local geometry around this, then the natural limiting object should be something that Aldous termed a sin tree. I'm assuming because these trees are quite sinful, but in fact, it's not because they're sinful, but sin means a tree with a single infinite path to infinity. Okay, so one would imagine that the limit objects in these sorts of models is something like this. So you have an infinite tree now, an infinite random tree. This vertex 0 is our analog of the randomly sampled vertex that we chose. And the limit object is we have a random tree hanging off this vertex 0. We have another random tree hanging off this vertex 1, which is vertex 1 is our idea for the parent of our randomly sampled vertex in our large tree tau n. Vertex 2 is the parent of our randomly sampled vertex in our large tree tau n, etc. Okay, and so the limit objects for these growing random trees, one would imagine, are these sorts of sin trees or random sin trees. Okay, and so this is what sort of was formalized in various ways already in the work of Jagers and Nerman, but is really nicely done in this is also very nicely done in this paper of Aldous. So we say that if you have a sequence of trees tau n, we say the sequence of trees converges in the probability fringe sense to some limiting infinite random sin tree. If the following thing happens, I should have said, for every fixed k, if you look at the fringe up to level k at your vertex, so you look at the empirical measure of the fringe up to level k for each vertex v in your randomly sampled tree. This should not be t, it should have been tau n. Tau n. So you look at these fringes up to level k. If these converge to the corresponding objects for your limiting infinite sin tree, for every fixed k, so for every fixed pattern, you end up getting this sort of limiting assertion. Then we say that the sequence of random trees converges in this probability fringe sense to this limiting infinite sin tree. And so the bottom line is so Jagers, Nerman, and all this. So first I should say, when you first look at this, this seems sure there's a definition, but how does one even prove something like this? But what Jagers and Nerman and then all this, what they showed is for a wide variety of random trees, this is actually true. Okay, so one can actually prove this. And so let me back up a little bit. So actually see if anyone has questions. Okay, no one questions on the chat. So let me back up a little bit and say, why should this even be true? And so what is one reason why this is true? And so this is what was sort of formalized in Aldous's paper. So remember, our goal is for this talk, the three models are sequence of trees which are growing. So at each stage, a new vertex comes in and decides to connect to a pre-existing vertex. So for these models, for tau n, let us, these trees are growing. They have some complicated probabilistic story about how they're evolving. So let us back up and let's think about, okay, let's forget about asymptotics, for the whole tree or local neighborhoods, etc. Let us just try to understand a much simpler object. You sample a vertex at random in your big tree, tau n. Let us look at the collection of individuals who came in time, after this vertex, and connected to either this vertex or some descendant of this vertex. Okay, so the people who came after this vertex and connected to this vertex or its descendants, its connections. So this is nothing other than the fringe of this vertex, this randomly sampled vertex Vn. So in my notation, this is just F0 Vn tau n. Now, we could reduce our goals and we can say, okay, maybe as a starting point, suppose let's just try to understand this is some random distribution on the space of trees, space of rooted trees, because I'm thinking about rooting this tree at my random sample vertex Vn. Can I just try to show that this distribution converges to some probability distribution as n goes to infinity? This probability distribution depends on the model, but can I try to show this? Okay, can one do this? And that seems like an achievable goal. And so for various models, this essentially boils down to showing that if you look at 1 over n, some v equals 1 to n, so you fix your favorite tree t, then you ask what's the probability that the fringe under this vertex v in your tree tau n looks like this fixed structure t. And our goal is to show this object converges to pi of t. Okay, so this is seems like an achievable goal. But what this paper, what Aldous in 96, what he showed is the following sort of amazing fact. Suppose you can show that this limit object that you get, this pi, is a fringe measure. I'm going to tell you what this fringe measure is, or what the definition of fringe measures are. And it turns out this definition automatically implies that fringe measures are convex on the space of measures on the space of rooted trees. Suppose you can show these are your limit object is a fringe measure, and suppose you can show that it's an extremal fringe measure. Suppose you can show these two things, then automatically, an amazing thing happens. So before I tell you what that amazing thing is, let me define these two things. So a measure on the space of rooted trees is called a fringe measure if it satisfies the following sort of, in some sense, stability property. So I need to define something before I tell you what the stability property is. So fix two rooted trees, S and T. Okay, so here, an example of S is over here. It's like one vertex, that's the root, and then there are two leaves connected to it. That is my S. And another rooted tree, T, I should have shaded this, but T is this just a single vertex. And so what is QST? So QST is the number of trees. You look at the children of the root in your tree S, and amongst the children, so look at the children of your root in S. So in this case, there are two children over here. And you ask, so each of these children have a subtree hanging off them. How many of these subtrees look like your fixed tree T? In this case, QS comma T is equal to 2, because for both the children of the root in S, their subtrees look like this fixed tree T. Okay, so this is called QST. So we say that a measure pi is a fringe measure if it satisfies this following sort of stability property. So for every fixed tree T, rooted tree T, if the following thing is true, you first sample a tree with distribution pi. So, and you look at the sum over all S, pi of S times Q of S comma T, this is equal to pi of T. Okay, so if the expected number of subtrees under your randomly sampled tree using this distribution pi, the number of subtrees of the root as the same distribution as sampling a tree with this distribution pi, then we say that this measure is a fringe measure. So this is the definition. And amazingly, lots and lots of random tree models. So critical random trees conditioned to be large, lots of things, continuous time branching processes, etc. Lots of limit objects in many different tree models turn out to satisfy the stability property. Now, if you look at this identity over here, it's easy to convince yourself that the space of all probability measures that satisfy this sort of stability property, it's a convex set. Okay, so if you have pi1 and pi2 which satisfy this, then alpha pi1, expected number of trees, isomorphic to, should be the expected number of trees, isomorphic to T. Well, right. So once you do, sorry, I'm just responding to the question here. So maybe I should have phrased this as X. So if you put, right, so expected number of trees isomorphic to tree, when you sample a random tree with probability distribution pi. That's right. It's the expected number. Okay, so the space of fringe measures is convex. So if you have a pi1 and pi2, which both satisfy this sort of stability property, then any convex combination of this also satisfies this stability property, if you just look at this identity. So then you can start, sorry, start talking about the collection of extreme points on the space of fringe measures. Okay, so namely the collection of probability measures pi, such that if someone tells you alpha pi1 plus 1 minus alpha pi2 is equal to pi for some fringe measures pi1 and pi2, this automatically has to imply that pi1 is equal to pi2 is equal to pi. So you can think about extreme points on this space. So how does one check that a specific measure is extreme? This is also there in this paper by Aldous. And so once again, many of the classical things that that show up in branching processes, etc., turn out to be extreme points according to this definition. But suppose you can show that, or your fringe measure is extreme, then what he basically showed is, suppose you're able to do these two things. You're able to show that the fringe measure converges in distribution. So for a sequence of random tree models, this F0, V, and tau n converges to pi, where pi is is a fringe measure, and it's also extremal. Then automatically two miracles happen. So the first miracle is automatically you get convergence in probability. So let me back up and let me remind you, what our initial baby goal is to show these expectations converge to pi. Okay, so in many examples, okay, the standard pipeline is you show expectations converge, then you try to show using concentration inequalities, bounded differences or something else, or direct variance computations. You try to show that the variance is small, and so in particular, you also get that these things converge in probability. You can remove this expectation over here. But what in this paper, what Aldous basically showed is you don't have to do this. Once you have convergence to this an extremal fringe measure, you automatically get that these objects converge in probability to this fringe measure pi. Okay, so that seems really cool. But further, once you've just analyzed the fringe distribution and you're able to show this, you get convergence to a limiting infinite random symmetry. So just analyzing what happens for the fringe distribution. So pick a vertex at random and study what happens to the collection of individuals who decide to connect to it or its descendants. If you're just able to analyze this, you automatically get convergence of the whole local neighborhood to some limiting infinite object that you can explicitly describe using this fringe distribution. Okay, these two sort of miracles happen. So let me try to show you how to use all of this in at least two of the models that I started this talk with. So the first model is this random tree model with choice. So I'm trying to tell you this model again, or remind you what the model is. And I'm just going to, for simplicity, I'm going to take k equals 2, and I'm going to think about the min model. Okay, so what does this mean? I'm just going to change this model a little bit. I'm just going to run it in continuous time. So instead of vertices entering at discrete steps, I'm going to assume that the following continuous time thing happens. So each vertex in the system creates a new vertex at rate 1. I do not mean it gives birth to a new individual. I mean it creates a new vertex. And this new vertex then looks at the whole configuration currently and decides who to connect to according to the rules of the game. So what is the rule of the game? So this new vertex that has been created samples two existing vertices at random in the current configuration and connects to the one with the smaller degree. That is the min model. Okay, so this is this random tree model with choice. Just the only change is it is now running in continuous time. Okay, so I'm going to tell you two sort of simple properties about this continuous time formulation. So the first one is, suppose you run this process for a large time t. Let Vt be, you suppose you sample a vertex at random. So I'm calling this continuous time formulation tau t. Sample a vertex at random from the tree at time t. And let's look at its age. So what do I mean by its age? So this vertex entered the system at some time. So let's call that time tvt, the time when Vt was born into the system. Obviously, it's less than t. So the age at time Vt, if you have local weak convergence, then the distribution, if you have local weak convergence of symmetry, if you have local, sorry, apologies, just looking at me. Local weak convergence of symmetry, then the distribution of the fringe, right. Yes, you're correct. So if you do have convergence, so if you do have convergence to, if you do have local weak convergence or symmetry, then yes, it is automatically a fringe distribution. But here we're trying to prove some things. Yeah. So here we don't yet know whether we have we're trying to prove that our sequence of objects converges to some limiting object. And so first, we're just going to look at a much simpler object, look at the fringe distribution, show that it converges to a fringe measure. And what Aldous's theorem basically says is then it automatically, you get this convergence, local V convergence, not just for the fringe, but the entire local structure. Okay, so backing up here, so the age of a randomly sampled vertex is, so it was born at some time TVT, and the age is T minus TVT. Okay, and so the first thing I'm going to tell you is the age of VT has, at least for large T, has approximately an exponential distribution, exponential mean one distribution. Okay, so why is this true? So my continuous time formulation basically means that the number of individuals in the system at time t exactly has the same distribution as the Yule process, because every individual is reproducing at rate 1 with this. So this is a pure birth process. And so if you look at the age of a randomly, if I ask, okay, fix my favorite number A, and I ask what is the probability that age of VT is greater than A, conditional on my what I know about the system at time t. So if the age of my randomly selected vertex is greater than A, that means it has to be in the system by time t minus A. So that means this is the total number of individuals at time t minus A, nt minus A divided by nt. Sort of standard facts about the Yule process basically means the numerator for large T looks like a positive random variable, W, strictly positive random variable W, times e to the t minus A, and the denominator looks like the same random variable W times e to the t. Okay, and so these W's cancel, and you end up getting e to the minus A. Okay, so the first sort of very simple fact is if you sample a vertex at random, then its age has this sort of exponential mean one distribution. Okay, so nothing very deep about this. But now let me do something with this. So let me ask the following question. So how long does it take for a vertex? So a vertex enters the system at some large time s. How long does it take for this vertex? So it enters the system. When it enters the system, obviously it's a leaf. How long does it take for it to change its status from being a leaf, namely being of degree 1, to having another vertex connect to it? So the first time for a new vertex to connect to it. So namely, its degree goes from 1 to 2. Okay, so suppose, so my vertex has entered the system at time s. And suppose at time s plus u, it still has, no one has connected to it yet. Let me then try to understand in a small time interval, s plus u to s plus u plus delta u, what is the rate at which a new vertex hopefully connects to it? Okay, so vertices are the rate at which an individual is born into the system is ns plus u du. Okay, because the process is growing. The process is growing proportional to the size of the system, which is ns plus u. So ns plus u du is the rate at which a new vertex enters the system. The probability that it decides to query this fixed vertex S is 2 divided by ns plus u, because it samples 2 vertices at random and asks them, what is your degree? So probability decides to query this fixed vertex S is 2 over ns plus u. And now what is the probability that it does decide to connect to this vertex? It will connect to it if the other vertex that it sampled is either has degree greater than 1, which is 1 minus P0 of S. P0 S is the proportion of vertices which are still leaves at time S. Okay, so if the other vertex has degree 1 or more, so degree 2 or more, which is 1 minus P0 of S, then this vertex will connect to this fixed vertex S. Or if the other vertex that was queried is a leaf, then we're breaking ties at random. So it will connect to this vertex with probability half. Okay, so this is the sort of total rate at which this new vertex, born in this interval S plus U in the small time interval, decides to connect to this fixed vertex S. Okay, so once you go through this algebra, Suppose for the time being, this is sort of seems reasonable. Suppose you assume that our sequence of random tree models are nice. Somehow you're able to show that the degree distribution converges. So in particular, P0 stabilizes around some number, P0S stabilizes around some number, P0. So assume that the degree distribution converges. Then what this tells us is the rate of this vertex S getting its first connection is approximately 2 times 1 minus P0 over 2. Okay, and in particular, the time for a vertex to go from a leaf to a degree, when I say degree, I mean at least one new child adding to it, to go from a leaf to a degree 1 vertex, maybe I should say degree 2 vertex, this has an exponential distribution with parameter 2 times 1 minus P0 over 2. That is the amount of time it takes for a vertex to get its first child. So now let me put these two things together, two ingredients. The age of a vertex has an exponential mean 1 distribution and a random, the amount of time it takes to go from degree to being a leaf, having no one connected to you, to having one person connected to you, having this distribution. Let me put these two things together. So what is our P0? So P0 is the probability that a typical vertex is a leaf, which again intuitively means that the amount of time it takes for this randomly selected vertex to get a new connection is more than its age. So the age is so small that you have not had enough time to get your first child. Okay, and so this should be, again, this is all, there's no rigor here because, but this should approximately be the probability that x1, where x1 is this random variable, an exponential random variable with this specific parameter, an exponential random variable with that parameter is greater than another exponential parameter, exponential random variable with parameter 1. Okay, and so this we can compute, assuming x1 and y are independent, this we can compute. So if you stare at this, we see we have an equation which connects P0 to P0 again. And so this gives us a way to uniquely find the solution for P0. Okay, and so it turns out you can, the same heuristic, you can do for other degrees, degree 1, degree 2, you can carry out this whole sort of intuitive argument to ask how long does it take for a vertex to go from degree 1 to degree 2, degree 2 to degree 3, and so on. And you end up getting a collection of fixed point equations. None of the details here are important. This is just to show you that there is a prescription for this. And at the end of the day, what you end up finding is you end up finding a point process. So you get a random variable x1, which I told you measures how long it takes you in this continuous time to go from no one connecting to you to at least to one person connecting to you. Then how long x2 measures after this, how long does it take for another vertex to connect to you? Hence, your degree, number of children is 2, and so on. So, but you could ask, who cares? At this stage, you've got fixed point equations. Maybe this will allow you to prove convergence of your sequence of random tree models to the degree distribution of your sequence of random tree models to some limiting degree distribution. So who cares about this? So what I'm going to do is, so this is a point process. You can think about a continuous time branching process with this as its offspring distribution. What do I mean by this? So in fact, I'm going to run this for an exponential mean 1 amount of time. But first, for people who don't know what continuous time branching processes are, let me just say what this means. So a continuous time branching process, once I've fixed this offspring distribution, means I start with one vertex, the root, and it gives birth in continuous time. So at random times, it gives birth to its children. So here, this vertex has given birth to its first child over here. Then I don't know if you can see my mouse. Luisa, do you see my mouse shaking? Okay. So then it gives birth to second child here, then third child here, and so on. And then the first child of vertex 1 gives birth to its first child here, second child here, etc. And so I run this process up to a random amount of time. This is this time y. Okay, and then I stop. I freeze and I look at what tree I end up getting. So I look at the genealogy of the tree that I end up getting. So vertex 1 has 3 children. So this is my root. The root has 3 children, which I've drawn over here. The first child, I've oriented them, from left being the oldest child and so on. The first child of the root has given birth by this time to 2 children. So I have drawn these 2 children over here, and none of the other people have reproduced by this time. Okay, so this represents the genealogy of my system. So we end up getting a measure on the space of rooted finite trees. Okay, and so what all this and going back to the work of Yagers and Nerman, what they essentially showed is that this distribution that I've ended up getting, it turns out it's extremal. It's an example of a fringe distribution, and it's also extremal. So what is the basic punchline? I just started by just thinking about a vertex and its descendants. How long did it take for this vertex to get its children? And this gave rise to a branching process. And because of the way that I constructed this whole thing, maybe it's not too hard for you to believe that one can push all of this to also show that the fringe distribution of a randomly selected vertex that converges to this distribution. But now, because of sort of this fundamental result in Aldous and Yagers and Nerman, starting from the degree distribution, I get fringe convergence, and then from fringe convergence, I automatically get that my sequence of random trees converges to a limiting infinite object. Okay, so just yeah. Okay, so I think I'm running out of time. Do I have like 3 more minutes?
Yeah, I think you can take 3 more minutes because we started
Okay.
with yeah.
Okay, sounds good. So I just I'll just spend 3 more minutes on maybe a slightly more complicated model, and then I'll stop. So this is this network model with delay. So let me remind you what this model is. So we fixed a distribution mu on the interval 0 to 1. A sequence, so for alpha is going to be 0. In general, it's an affine preferential attachment term, but just take alpha to be 0. And theta i's are IID with the distribution mu. And so the basic model is vertex n plus 1 only has information up to time n times 1 minus theta n plus 1. And so this vertex v connects to the information that it has. It looks at that tree and connects with probability proportional to the degree of a vertex in that tree and its degree in that tree. Okay, so once again, I'm going to do this in a continuous time formulation, and one has to be a little bit careful. And so the starting point is for us to understand in words, not math, what these thetas represent. So in my head, theta represents, or 1 minus theta represents the density of information that I have at any given point in time. Okay, so that's what 1 minus theta represents. And so this will show up in the next step. So what I'm going to do, just as in the previous formulation, is I'm going to think about vertices entering the system in continuous time. Okay, at each vertex gives rise to a new individual at rate 1. So vertices are entering the system according to the times of a Yule process. And now when this vertex enters the system, it has to make a decision. How do I go from my discrete model to my continuous model? Well, remember my interpretation of my 1 minus theta is the density of information that I should have. So what this means is in my continuous time model, I should have information not of my system at time t, but my system at time t minus some zeta. And the relationship between this distribution theta and this distribution zeta, theta and zeta, or xi, whatever, is this nt minus xi divided by nt, that is the density in continuous time, should be like 1 minus theta, which suggests that this distribution zeta is minus log 1 minus theta. Okay, so this is going to be my model. A vertex comes in, it samples a vertex in the tree at time t minus zeta, and then decides to connect with probability proportional to degree. Okay, and so once again, I can ask, so the age of a randomly selected vertex, once again, has an exponential mean 1 distribution. And I can ask the same question. Suppose a vertex was born at some large time s. And suppose up to time s plus x to s plus x delta x, it hasn't had any children. So how long does it take for its first connection to form? Okay, so suppose there's no children up to time s plus x. What is the probability that in a small time interval, s plus x to s plus x plus delta x, a new individual does decide to connect to this fixed vertex s? And what's the bottom line here? Once again, lots of individuals will be born in this small time interval s plus x to s plus x plus delta x. For each individual that is born in this interval, if its delay is too large, this vertex s is going to be invisible. So the delay cannot be too large. So how do I formalize this? So if a vertex U is born in a small time interval, it experiences a delay. This delay is, it should not be eta, it should be the zeta, but anyway, it experiences a delay, eta, which has this distribution, minus log 1 minus theta. It experiences this delay eta, and conditional on this delay, the probability of it wanting to connect to this vertex S is, well, the delay has to be smaller than this X. Otherwise, this vertex S is invisible to it. But if it is visible, then it turns out, because of preferential attachment, the total number of edges present in the system at that time is 2 times the size of the system. So nt plus x minus this eta u. And okay, so this is the probability that that fixed vertex u born in the small time interval does decide to connect. Okay, and so I'm going to more or less end by telling you what this implies. So what you can basically write down, again, without any rigor here, there's no rigor. This is just, just following your nose and trying to see, okay, what does this mean? It suggests that I have lots of individuals, n s plus x delta x many individuals born into the system in the small time interval, and the probability that each one of them does decide to connect is very small. I have 1 over nt plus x minus eta u, okay, something, but probability of connecting is very small. So hopefully there is some sort of Poisson distribution in the background. So, and if the Poisson random variable is greater than 0, that basically tells me someone did decide to connect to me in this small time interval. So you can write down what this entire thing suggests. And at the end of the day, what it suggests is the hazard rate, namely the conditional probability that given no one decided to connect to you up to that stage, someone does decide to connect to you in this small time interval. You can write down a hazard rate for the time of the first connection to you. Once you've done the first connection, you can do second connection, third connection, etc. And but it turns out all of this intuitive argument over here, you can make it precise. It is correct for the discrete time model. And it shows that the sequence of random tree models with this delay converges to a limiting infinite object, once again driven by a continuous time branching process. And the continuous time branching process has this sort of offspring distribution. And offspring distribution we got using this very heuristic calculation. Okay, so yeah, so that's it. I think I'll stop over here. Happy to take any questions.
So thank you very much, Shankar, for the very nice talk. So do we have questions? I think people can just unmute themselves and ask a question or raise a hand. Let's see. I can start breaking the ice with one question indeed.
Okay, yeah.
So actually, you were very nice, because I think you were hiding a lot of nasty, like difficult computations in the way. But it seems that going to this continuous time, it's helping
Yes.
out with these discrete models. Is it just to give the intuition, or it's also something that you use to just
Yeah.
nail down
No,
that?
no. It's a great question, and I have been so yeah. So there is a story here. So when I was a grad student in Berkeley, I was like learning this Aldous fringe convergence, and then preferential attachment was, people were thinking about this in 2007. So the standard preferential attachment models, many of them you can embed directly into continuous time, and you can use results of Jaggers and Nerman, etc., to get lots of results. And so I'd started doing some notes over there, but there was nothing very deep about these set of notes because many standard models you can directly embed into continuous time, and okay, then it's okay. Sure, you get results, but you're just using things that these great people have already established. Now, going back to your question, so the last 3 years, so I've shown you 2 models here. The third model, this nodal attribute model, also there is a more complicated multi-type branching process that arises in the limit. And I still don't understand why moving into continuous time. So these models, there is no, let me go back here. Here I wrote down some heuristic thing, zeta should be related to my discrete time model like this, because this is the density of information. And then I went to town doing some heuristic calculation. But there is, intuitively, there is no reason, at least in my head. I don't know why once you move to continuous time, so many calculations become super easier. I mean, super easy. But at the end, you're able to write down what the limit is for these models which cannot be embedded directly. You're able to write down what the limits are, and then once you know what the limits are, then trying to prove that rigorously that these are the limits takes a lot of work. So it is not it's not very easy necessarily, but at least now you know what the answer is, and then now you have to get there. But I don't know. That's a good question. It's yeah. So I also have been struggling a little bit as to why this is the continuous time formulation makes lots of these things much easier.
Mm-hmm. But it's not enough somehow. It's something that then
No. I mean, it was enough in 2007 and 8 when this classical preferential attachment, because we directly embed them.
yeah.
None of the models I've shown you, uh, none of the three models in this talk, you can necessarily directly embed them. But
Okay.
yeah,
Okay.
or
I see.
yeah,
You. Other questions? Yeah, I think Noah raised.
yeah. Go ahead.
So please unmute yourself. Yeah.
Could you say a bit more about the motivations for studying these tree growth models and the
Yeah,
centuries?
great question. Sure. Okay. Yeah, okay. Great question. So, let me go back all the way to the beginning. So, um, okay. So random tree models or network evolution models in general, again, preferential attachment, etc. Lots of very deep work. I would say the last maybe 3 years, the things that people are really interested in are models where you have limited information. So I'm going to say something which is actually false. So the classical preferential attachment, when you first stare at this, vertices come in and connect with probability proportional to degree. It seems like one needs global information about the whole graph to make your decision. You're making a probabilistic decision, but one needs global information. In fact, this is not quite true because you can view this as an edge copying mechanism, or you sample a vertex at random and either connect to its parent or itself. So it's not quite true, but many preferential attachment models somehow seem to look like they need global information. So the way that people have been moving away from this is trying to understand network evolution models with limited information. And so there are two main mechanisms. Again, they overlap, but two main mechanisms in how people have been implementing this in the applied probability community. The first one is you sample vertices at random and explore local neighborhoods around them and then make your decision. Okay, so that's one mechanism of, okay, you have limited information, what do you do? The second way people have been doing this is, okay, you don't have the entire information of the graph at time n, but you have a time delayed snapshot. So the first model is this tree model with choice, where you randomly sample a vertex. I mean, an example, sorry, is not. You sample a vertex and look at a local neighborhood and decide what to do. This is this tree model with choice. And this delay tree model is the other implementation. So yeah. So I've shown you two implementations of this sort of, this general thing that people have been interested in for the last 5 years, let's say.
Great, thanks. Other questions? I think we have maybe 1 more minute for like a quick one, if someone has one. But it has to be quick, I think. So, yeah, so it seems that maybe, I mean, since we are a bit short on time, I think we can thank Shankar again very much for this great talk. It was very inspiring and nice.
Okay, thank you. Well, yeah, you can thank your next speaker
Oh, yeah.
for this one. Oh, and also, yeah, if you do have any further questions, please ask him. Don't ask me. Anyway,
Yeah.
okay.
And it was also a great introduction for our next speaker, indeed. So thank you for doing this, Shankar. So yeah, well, thank you. I think we can maybe take a very short break. Okay, yeah, no, I think we can start. So welcome back to the second session of this first one word probability seminar of spring 2025. And so we are very happy to have David Aldous from University of California, Berkeley speaking. And we are very much looking forward this talk with a very nice title, which is, so David will talk about obscure results and open problems, some of his favorites. So please, you can start.
Okay, so thank you very much. It's fun to see a number of familiar names in the audience here. Okay, let's how does this work here? Okay, now my thing is being annoying. Let's do it that way. Okay. The subtitle is more interesting here. These are all sort of a bunch of different problems where, I've got started. I've done a first step, but I really want some smart younger person to continue. I've gone as far as I can. Uh, We'll probably get through all six of these. Some of them are loosely inspired by real data. I always like having some data to show at the beginning of a topic. I will for some of these. It's not intended as serious statistical modeling, just as sort of inspiration for questions. The "Are you smarter than an AI" is an interesting story, I'll say in the middle here. So let me just jump in. So here the title says it all. So this is just a math theory question. If I take a complete separable metric space and take a probability measure on it, and then take two independent samples from that probability measure, I can then look at the distance between them. It's a metric space, and that distance has some distribution on 0, infinity. It might be 0 if it's atomic. And the question is, what distributions theta can arise in this way for some probability measure on some complete separable metric space? And of course, there are a lot of metric spaces and a lot of probability measures, so we're clearly going to get a lot of possible distributions theta. Curious question, because this question could have been asked anytime in the last 80 or 100 years, and apparently no one has actually thought about this question, or maybe they thought about it and just nobody's written anything until us. So in particular, we have a conjecture and a partial result. So the conjecture is that almost anything works in the following sense, that any probability density function whose support contains 0 can arise in this way. And partly the reason we kind of believe this conjecture is that we have a theorem that gets close to it. So the theorem says that, again, for any such probability density, if you give me a density whose support contains 0, then we can find feasible densities that approximate it arbitrarily well. And this is a funny result for several reasons, because your first thought in this problem is, well, it's a metric space, there's a triangle inequality, the triangle inequality should impose some restriction. But basically, the theorem says it doesn't. I mean, there's nothing global going on. So somehow, if the conjecture wasn't true, then that would have to be some sort of local property of a function that stops it being true. So anyway, the proof of that theorem kind of uses the first idea you might think of, which is to think of a construction where our metric space is a tree. Of course, having a metric space being a tree, there's a unique path, so we sort of understand distances on trees very well. So you start off realizing you can do a construction involving an atomic, a sort of a purely atomic distribution theta that just supported on a finite number of points. You can do a tree construction for that, and then you can smooth out a bit. But we really gotten stuck as far as we've gone with tree constructions of a metric space. So we really need a new idea. What's weird about the question is that normally when you encounter a metric space, there's a set of objects that's somehow given to you, and then what you have to do is define the distance on it. Whereas here, we're sort of not given a set for the metric space. We're just sort of given a distribution on 0, infinity, and we have to sort of totally invent out of thin air a metric space, and we don't know how to do it. Again, for a general distribution theta on the line, it's necessary but not sufficient that the support contains 0. The necessity is a simple compactness argument that is our probability measure on the space is almost supported on a compact set, and therefore there are small ball. There are always arbitrarily small balls with non-zero probability, and therefore two samples might be in the same small ball and might be close together. So that's here. But one first thought might be that because that's the only necessary condition, but there's a sort of weird type of example that shows that isn't true, but we don't know any other obstacles here. So again, that's all I'm trying to say. We have a problem and it needs a new idea. I'm not going to click on them, but the links here are live. This will go to find given papers. I'm not going to do it now. I might get stuck and not know how to get back here. Okay, that was quick. Topic 2, probability distributions on what I call routed planar networks. I made that up. So the little story I'm going to tell, the older members of the audience will remember that in pre-electronic era, when we give talks on an overhead projector and transparencies, when we'd write on a transparency and that would get shown up on a screen. So I want you to imagine two old things, this transparency and a paper roadmap. And what I want you to imagine doing is putting down a number of points on your transparency and then putting the transparency over your paper map. And then for any 2 points you've drawn, I want you to draw the route by road from one to the other. Okay, so that's what my imagining sort of 7 points on my transparency, and I put this on a map, and I've drawn all the 7 choose 2 routes here, and sort of put them together as a picture here. So why am I doing this? Well, I want to imagine a sort of mathematical version of a road network. So the analogy is that, in Shannon type theory, we imagine sort of English language text as a sort of stationary random process, or as a realization of a stationary random process for entropy, etc. So I want to imagine the real road network as a realization of some random process, and the distribution of this random road network is specified by these finite dimensional distributions, the subnetworks on an arbitrary number of points. And in particular, I want a model to be scale invariant, meaning that the size of the topology within a window has the same distribution regardless of the area of window we're looking at. So again, the analogy is sort of random walks and Brownian motion. Simple random walk is asymptotically but not exactly scale invariant, that is self-similar. If I want things to be exactly self-similar, I have to be working in the continuum. So we have this rather abstract theory that I'm not going to say anything about other than the words here, but we're imagining this random network in the continuum plane, and a realization has a unique route between almost all pairs of points. Now, do these things exist? It's not actually obvious that those things exist, but you have to take it on fact that they do. And so as part of that, again, I do lots of research with undergraduates, and the research isn't so much proving theorems as sort of doing coding, etc., or collecting data. So we actually have some data on these sorts of little networks. And of course, instead of the transparency and the paper map, we're using Google Maps and doing it all virtually. So here's the sorts of things I have undergraduates doing, which is you to take 4 points roughly in a square at random places in the United States, and we actually do this. We get Google Maps to draw the routes between all the pairs, and so this is sort of easy to do. And the point is now we see some number of different topologies, so we're not going to try and, in theory, you could look at all the distances and lengths, but we're just looking at topologies here. So without precisely defining what I mean by topology, one can just sort of look and start drawing on a piece of paper, and in a very naive way, we listed all the different topologies you could get here, which we think there are 71. So I have little drawings here. There are yellow paths and so visible here, at least to me, but we have a paper that just goes through manually looking at all the possible topologies. So this is sort of a kind of curious structure here. I mean, obviously, in one sense, these are planar graphs, but in another sense, that we have different information. These are sort of planar graphs on sort of 4 little leaves here, but where we have the distinguished routes, just like sort of a subway, a map of subway lines here. But there are a number of things one can do. So, of course, we can compare this mathematical list with what we actually see. And what we actually see, as you can imagine, is a very non-uniform distribution on these 71 topologies. So, again, that's as far as we've got. I mean, what we've done is this sort of manual listing of what can happen. There are many more questions that you can ask. I mean, instead of saying, are 2 realizations giving me the actual same topology or not? Well, we're just doing this by eye, but one would like a mathematical way of coding or naming the different topologies so one could see whether 2 are the same or not. And then can you get beyond 71 by counting and enumerate some version of this? More interesting to me is that for any kind of simple combinatorial structure of size n objects, you usually have natural families of probability distributions of that, not just the uniform one. So can we have a sort of natural non-uniform distribution on these things to try and fit real world data to? Can one kind of constrain the map can one constrain one's model to try and simplify the model? So in any random model, probably all these 71 topologies would come up sometime, but can you sort of forbid some of them and get an easier theory? And finally, we actually have 2 explicit models of fully scale invariant networks. So in each of these models, there is some probability distribution on these topologies, but somehow the models are, in some sense, explicit, but also limits of things. So it's hard to do actual explicit calculations with the models. So again, you can read more about that, but it's just a sort of an interesting new sort of combinatorial structure to think about. I don't know if I said before that all these links will go to relevant papers. Okay, going quickly here. Topic 3, actually related. This wasn't planned on my side, maybe on Shankar's, but sort of related to what Shankar was talking about, fringes of trees. So at the bottom, you can't read it, but this is the phylogenetic tree showing relationships between, I think, 77 species of parrots, mostly in the Amazon jungle. If I'm talking to a British audience, I launch into a theme of humorous comments based on the phrase dead parrot, but I'm not going to do it here. It's a little, doesn't work, might not work so well non-live. Anyway, it's very easy to find things like this for yourself. If you go to Google Images and type in phylogeny of parrots or phylogeny of felines or phylogeny of sharks, etc., phylogeny of any group, they'll just show you pictures like this, which is gotten from various scientific papers. And what's curious as a sort of math structure is this notion of very uneven splits here. As you go down here, a split often has a small group on one side and then a large group on the other side. And that's a universal feature which has been observed but never satisfactorily explained. So I don't have an explanation of it, but one can sort of make up a model. So we have a random tree model, which again, I'm not going to say the math. It's mathematically simple because I just want to say, any group of n species is getting split into some number I and some number n minus I of splits. So we just need a probability distribution on the size of splits, and we're doing these beta distributions, beta with I equals -1. So we split proportional to 1 over I times n minus I, which obviously does designed to give us very uneven splits. And that turns out to be critical in a certain sense. So it's a mathematically natural, though of course not at all biologically natural model. And it's designed, this is a simulation of the model, and you can see it has roughly similar behavior. And if I showed you simulations from more standard tree models, they would be sort of substantially different from these two pictures. However, so this turns out to be a mathematically interesting model. So we have a sort of ongoing project both with Svante Jansen and with Boris Patel. We have 3 authors, average age 75. So there's some serious about, I first thought of this model around 1996. So I spent the however many years that is, 30 years trying to get a young person to involved, and no, but just Boris and Svante instead. So anyway, where am I going with this? Forget what's up. So that's my ongoing project. We have this model. It has a critical value. So in some sense, there are 0 free parameters. So this model just predicts numbers here. Now, there's a bit of a sort of philosophical point here, which I kind of, an argumentative point, that one often sees papers where they've gotten some sort of data and we say, here's some data, and here we come up with a model that more or less replicates this data. So what does this prove? Well, maybe your first 17 models didn't predict this behavior, and the 18th one does. So in a sense, this is just saying you've been persistent in trying different models till you get the one that fits. And persistence is admirable, but it's not so convincing. So in some sense, the acid test of a model is whether it fits something that you weren't trying to make it fit. So our model was deliberately designed to sort of fit this large-scale structure, but of course we can always also study the fringe structure of what the small fringe trees look like, and that's not something we were trying to do. So the answer is we have these numerical computations. So we're doing, again, what Shankar was talking about, that if I take a particular leaf. So I want to imagine that there's a big tree on 1,000 leaves, but I'm just sort of picking one leaf and looking at what happens locally. Then this a leaf like this is first in this triple. It's sort of first in this tree, which is like that. And then as I go further up, this leaf is one of the leaves in this tree, which is, what is that tree? Which is this tree, and then when I go up further, it's in one of these trees. So any given leaf is in a sort of increasing sequence of some of these trees, and we can actually explicitly calculate in our model. This is where the big tree, of course, the size is going to infinity, but this proportion, 60% of all the leaves are so one of these pairs, and 45% of the leaves are in one of the leaves in a tree like this, etc. And these are just given by recursive formulas. In other words, there's some theory that gives us the actual size of the distribution on the size of these trees, and then the model says that the model tells us that within a given size what the frequencies of different shapes are. Okay, so that's as far as we've got, but the trouble is that sort of we can only calculate these things numerically, that there's some slightly intricate recursion which is easy to simulate, but we don't actually understand. So in other words, we understand the proportion of leaves that are ever in one of these fringe trees of size 6, but we don't understand except numerically what the particular probabilities are, and of course we need to do calculations. So the point is that there are sort of fun little combinatorial questions you can ask about this structure, because remember, when the background tree has 1,000 leaves, there are going to be lots of copies of this in the fringe and lots of copies of this in the fringe. But one can ask these combinatorial questions along like the birthday problem or the coupon collectors problem. What's the largest tree that appears twice somewhere in the fringe? What's the chance that two trees have exactly the same shape, and so on? And these are non-uniform birthday problems or non-uniform coupon collection problems. And of course, in principle, they're well understood and simple, but they're well understood in terms of actual non-uniform probabilities, and we don't have a good theoretical grasp on those. So again, if we look at the asymptotic proportion of leaves in a given shape of tree, we can calculate numerically, but we don't know analytically what the sets of probabilities are. So we don't know in our 1,000-leaf tree, we don't know how many different fringe shapes there are. Okay, let's move on. Topic 4, nearest neighbors of nearest neighbors. It's one of these elementary facts you have to realize somewhere, that in any spatial context, you have a nearest neighbor, but you might not be the nearest neighbor of that person. Their nearest neighbor might be someone else. So maybe the simplest question of this is a Platon point process in the plane. Then you can just write down a formula for the chance that a point is the nearest neighbor of its nearest neighbor. It's just an integral of an exponential of a Platon probability. One could, for comparison, one can ask this different question. If I put an even number of uniform random points in a square uniformly, what's the chance that every point is its nearest neighbor? This, by some additivity, goes down as some power to the n. Whether this beta is somehow the same as this c seems to be a subtle question. It may or may not be. What's the effect of knowing that some other points are close to each other? Does that impose any dependence on what's going on here? However, there's a sort of combinatorial version. Again, this is a made-up math problem, but it's just intriguing. So RNN is this property, reciprocal nearest neighbor. You're your nearest neighbor's nearest neighbor. And the combinatorial version is just a kind of complete graph with IID lengths on it. So I have the complete graph, IID edge lengths, then the distance to a neighbor is just the length of the edge. It's easy to see, therefore, that, so I'm now doing some very little calculations here. What's the chance that vertices 1 and 2 are of each other's nearest neighbor? And well, when you think about it for a moment, there are 2m minus 3 edges which are incident at 1 or 2, and this is just the event that the edge between 1 and 2 is the smallest of all these 2m minus 3 edges, so we know what that probability is. And therefore, by sort of summing over vertices 2, we know what the chance is that vertex 1 has a reciprocal nearest neighbor. And now we come to the next question, that if I have an even number, m equals 2n, of vertices, it turns out that we do have this nice formula for the probability that every vertex is its nearest neighbor. These double factorials come up in tree contexts too, so I'm not sure if there's one thinks this is sort of isomorphic to some other result, although I don't see exactly what it's isomorphic to. It can be shown as an interesting phrase. So I'm going to digress for fun here for a moment. In a live talk, I asked for a show of hands at this point, which I won't try here, but some of us would have gotten an email like this. I've copied something from an email, September 2024. The grandiose title, you have a science fiction title here, Humanity's Last Exam. So they want you to come up with questions that AIs cannot do currently. Now that, of course, sounds easy at first sight because, well, ask them what's the meaning of life. But somehow, no, there are ground rules. There are ground rules here. And of course, the interesting thing is a bit of arithmetic down here gives you sort of $500,000 in prizes here. So some of us are a bit competitive. So how hard can it be to make a problem that AIs can't do? And this isn't actually intended to be mathematics. So this is on anything. But okay, so how hard can this be? And again, it's hard because of the side conditions. So explicit or implicit side conditions for your sort of entry to be allowed. So firstly, you have to know the answer. So somehow you can't. We're trying to find things that humans know the answer to, but that AIs don't. So as a practical matter, the answer can't be found on the internet because AIs have read the internet. So you have to come up with a question that has an answer that can't be found on the internet. And of course, you can't say what happened on your 5th birthday party because that's not sort of open knowledge. So it has to be answerable in principle by an sufficiently intelligent human or AI. They want you to be able to state a question in words, meaning you can't use too esoteric mathematical concepts. They're not going to count. They don't want trick questions. So you can ask nonsense questions, or you can ask questions. But they want questions that someone might actually ask. And then when you do this, there's a kind of interface to pose these questions, and it'll put the questions to 5 different AIs, and they have to all give incorrect answers. So there are these hoops you jump through for your question to be accepted to entry, and then finally, the awarding of prizes was done by human judges, of course, but not without any clear specification, but they're wanting a wide range of sort of interesting topics here. So it's harder than it looks. You can go to their site and see some questions. Of course, mathematics is the easiest topic to do this. So it ended up that almost almost half of the accepted questions were math or CS or something similar rather than humanities. So the humanities ones are more interesting. Anyway, so I tried 10 questions and sort of 6 of them went through these hoops of they'll accept it. I was, imagining, what am I going to do with $5,000, but slightly overconfident. So I and a few other mathematicians I know got $500 prizes. And of course, where is this going? The question that actually won was this: it can be shown question. The AIs came up with amusing different answers, but the AIs weren't quite smart enough to figure out this formula. So I think you can probably still play this game on the site. You won't get it, you won't win any money, but you can still sort of ask. I mean, I actually abused this by other searches I wanted to do, not for the competition, but instead of asking one AI, you can ask 5 at once. So why not do that? Okay, moving right on. Where am I? Somehow I've lost the. Okay. Oh, okay. So this is continuing with the same problem. There's a general small type of kind of combinatorial probability problem of the first of this abstract type. If I have an n-vertex model of something like the Erdős-Rényi model, and I have an event that's exponentially unlikely, like my realization of Erdős-Rényi is in fact the complete graph, that's unlikely, but I can ask for the largest subset of vertices such that the induced substructure of that has this unlikely property. So of course that's the maximum clique problem. But when you think about it, there are some other problems with the same general structure. You can ask the largest common substructure. So I can say you take 2 independent copies of Erdős-Rényi. Well, what's the largest subset of vertices such that, again, vertices labeled 1 to n, what's the largest subset of vertices such that the induced graphs are the same? And a little thought tells you that's actually the same problem as this one, slightly disguised. And the same thing happens for the idea of a longest increasing subsequence of a random permutation. It's sort of exponentially unlikely that when you have a random permutation, you actually get 1, 2, 3, 4, 5, 6, 7, etc. You get the increasing one, but you can then ask for the longest increasing subsequence of a random permutation. And if you think about it, that's the same problem as taking 2 independent random permutations and asking what's the largest subset of vertices which are in the same order in both realizations. So there are two types of very similar but not exactly the same thing here. And so as a new example, I kind of know about 4 examples of this, but making a 5th example is our reciprocal nearest neighbors within our model. What's our model of a complete graph with IID edge lengths? What's the sort of largest vertex subset within which every vertex is its own recursive nearest neighbors? So again, that's the sort of problem. You can easily see this should go up linearly with n according to some constant c. We don't actually have a proof of that. None of our general tricks like subadditivity or inventing a limit structure work, so we don't actually know that's true. Again, one's instinct is that this is on the boundary. That there are some problems of this form where we see you're never going to you'll never have a formula for C. There are other ones where you're confident there should be a formula for C. This to me is sort of right on the boundary where I wouldn't make a large bet either way on whether there's a formula for C or not. What we've done is kind of the obvious first steps in this type of program, the first moment method, i.e. calculating expectations, numbers of solutions gives you some bound. You get a lower bound by just thinking of a greedy algorithm for producing a subset with this property. You have a few usual tricks in this world. As I said, start a project for grad student is to sort of to see how you can get further with bounds. But again, we need a new idea for either studying this or for improving on greedy algorithms here, and it just seems a sort of a doable project. Okay, how am I doing? Okay, 5 minutes.
Yeah, 5 to 10 minutes.
5 to 10 minutes. So I'm going to go to topic 6, which is more fun. Just a second, and less in there, less mathematical. So here we are. I want to, again, toy models of real world. I want to find a qualitatively realistic model for a subway network. So this is like my phylogenetic trees. So there's some particular aspect that these things have, and I want a simple model that reproduces one observed effect. I mean, the background here is the sort of human world is very non-spatially homogeneous because you have cities and rural areas and deserts, and the population density varies in some great and not very modelable way. So that sort of our custom of thinking of spatial problems as taking place on a two-dimensional grid or a Poisson process of constant rate just doesn't work very well. So what's a context where variation of population density matters? And then I'm thinking of large 20th century cities with a sort of dense center, and then suburbs getting less and less densely populated, and people moving around within that world. And of course, that's the context of subway networks and big cities. So Wikipedia, for some reason, makes up these examples. I'm not sure are very realistic actual subway networks, but just to do it. But the issue is sort of what do we, from common sense and experience, what do we think a subway network should look like? And of course, so here's a current version of the famous London Underground map, which has sort of a big subway network. They've cheated and started putting in some railway lines that aren't really the subway. But anyway, and this is sort of what you'd expect, that there's a central core which is rather densely connected, and then when you go out from the central core, you start branching out towards the end here. So this rough idea, a well-connected core, often as in London with a circular line around it, and then branches go out. So our question, again, it's one of these questions I had as a sort of undergraduate project that wisely no undergraduate was ever willing to do, was to say, can we make up some toy model of what an optimal network should be in some sense, and can we find a toy model within which optimal networks are like this? And to cut to the chase, we can't. So I actually was interacting with Barthélemy, the sort of world expert on this sort of thing, for doing via statistical physics methods, and the two of us couldn't do this. So I'm going to tell you the model that doesn't work. So your job is to find a better model. So the model that doesn't work is, well, so there's a density. So people are making journeys from one place to another. So we need a probability distribution on where are you coming from and going to. So we're having a Gaussian or a power law. Density doesn't make too much difference of where people are going from. And a simple model, the point of a subway is you can travel fast on it. So there's some speed you can go on the subway network, but you also have to get to the subway network. And we're imagining you walk or bicycle or take a bus, but whatever it is, it's slower. So basically, we have a one-parameter model, which is the ratio of how much faster the subway is contained uh, compared to the alternative. And individuals are seeking to minimize their journey time. So they either sort of have to get to the subway network, get through the network, and get off it. Or, of course, it might be simplest not to use the subway network at all and just go directly. So everyone optimizes the journey time. Uh, and we're wanting to design the network of a certain length, which optimizes this sort of average journey time. So on a picture, I've drawn a dashed line around a center containing 40% of the population. And these are the optimum networks we found for different lengths. So one unit is the radius of the circle containing 40% of the population. This is length 8. As you can see, you've got six edges here whose length is a bit more than 1, so that's 8. And we do this sort of separately for different lengths, and we get these as optimum amongst the networks we thought of. We get these shapes. And in one sense, this is sort of nice in that these are rather plausible, except it's just not what we expected to find. This is not what the real world things look like. And using my own kindergarten level Python to do these things, as well as my whoever my statistical physicist person did, we couldn't actually do this for very large networks. I mean, minimizing over optimizing over the space of all networks obviously is an impossible thing to do, because here we're not talking about topology, we're talking about actual distances and things. So you kind of an infinite number of networks. So it's a computationally hard thing to do, but we lack efficient code to do it for very large networks, but it doesn't seem to be working. So there's, even though our model seems very plausible as the first toy model, the problem is to find a better model, but kind of a one parameter model. You can, like all jokes go, you can fit anything with 6 parameters, but is there a one parameter model that actually has this desired feature of well-connected core and branching out. And okay, thank you. I will stop there.
Okay, so thank you very much for this very nice talk. And as before, we will start with questions.
Do you
Great.
hear me?
Yes, we can.
Thanks. So my question, actually, it was a fascinating talk. The question relates to the nearest neighbor problem, this RNN. You were asking about possible formula for ideas for the formula of the C for the constants in the distribution of the size of the what you had. So basically, I was wondering, how do those constants depend, or do they in any way on the shape of this n vertex model? One would assume you have this connection just to the number of vertices n, but are the constants in any way dependent on different types, distributions of this realistic model? Thanks. Could they be expressed, and could this be any idea there?
Yeah, no. The distribution of the edge lengths doesn't matter. This is all distribution free because we're just talking about maxima and minima.
So it doesn't depend at all.
Right. I always use exponential random variables as a sort of generic generic for non-negative things. The combinatorialist tends to use sort of the uniform on 0, 1 as a sort of default probability distribution, whereas you shouldn't. It's always better, almost unless you're dealing with things that are intrinsically bounded above, your sort of default choice should be exponential, says me.
What are then the C1 and C2? You probably computed them?
They're in yes. If you click on the link at the end of the topic, you'll
Sure,
see it.
sure,
I mean,
sure.
they're just numerical. They're not sort of a nice formula.
Okay, thanks.
Yeah.
Other questions?
I was wondering, could you talk more about these 71 different road patterns and how you there are so many and what they look like? I was, as you said, it was hard to see the yellow, but maybe you
Yeah.
can.
Boy, now, if I were competent at drawing things online, I'd do it. You, yeah, basically, yes, we're drawing 4-2-2, which is 6 lines, and well, you kind of start off with two diagonals, and then there's basically two possibilities because they either sort of cross at a degree 4 thing, or they sort of, or you sort of join a line and divert from it. And then when you sort of start drawing the other lines, you just see you have a lot of choices because sort of you can either merge with another line or go straight across it, etc. Yeah, so it's a bit complicated to say. Again, it surprised us there were 71, and I mean you can be fussy. As I said, what I did might not stand up to uh, any very sort of severe test of when two things are the same. So we're counting sort of obvious symmetries, but there might be that two things we've counted differently should really be considered the same. Again, that's why we'd like someone to someone to look more systematically at what we've done. Yeah.
Okay, thank you.
Good. So there is a question in the chat about topic 5. I don't know if you want to unmute.
Okay, let me find the
yeah, or
chat
if you just want, yeah.
Somehow, just a second. Okay, chat. If I
Yes.
understand. Okay.
The question is just, could you talk more about
Yeah,
that?
just brief.
Oh,
We can read it for you.
Yeah,
okay,
sorry.
oh, that was in there. Okay, I'm seeing at the bottom. Where am I going to? About topic 5. Okay,
Yeah, the
yeah,
one that you skipped.
yeah. I'll talk very briefly, which is again, I have a graph with generic real edge lengths, and there's a deterministic walk on that graph where you sort of move at speed 1 along edges, and anytime you reach a vertex, you then say, I'm next going to go to the closest vertex I haven't visited already. Now, that might not be a neighbor. You might have visited all the neighbors already, but still, there's some closest vertex, even if that may be some distance away. So eventually, on a vertex n graph, eventually you visit every vertex, and the issue is to sort of understand how long that takes. Again, that's a deterministic question on a deterministic graph, but of course, being a probabilist, I want to apply this to random graphs and look at this distribution. So this is this analogy. There's a large literature on cover times of random walks on graphs. So this is a different sort of cover time, and in particular, if you think of typical distances to nearest neighbors as order 1, then the length of the path has to be at least order n, because you've got n vertices. And the issue, what we understand is on the order of, we understand orders of magnitude. We kind of understand conditions such that the upper bound is order n, but we don't understand anything at all more than orders of magnitude. So that was the problem.
I see. Thanks. Other questions? Let's see if someone wants to ask, can just raise their hands or unmute themselves. So let's see. In the meantime, I do have one indeed about your your description of this phylogenetic tree and the splitting. Can you, if I've understood correctly, you're describing the splitting, so from top to bottom somehow.
Yes.
Can you build some similar or maybe even a matching model to describe this type of tree from, let's say, bottom to top, so some sort of
Oh,
coagulation?
yes. I mean, that essentially is exactly what we're doing. Yes, we have this, as Shankar was saying, we have this general theory of fringe distributions, and that's exactly what I was talking about. Everybody draws pictures differently. This is part of as you may have noticed, in trees, but sort of. Yeah, as I was saying, any given leaf is in a sequence of it might be in might be in this tree and then in this tree and then in this tree as we go up. So this is sort of a different visualization. I haven't drawn the sort of infinite line. Yeah, but it's very much the same ideas here. Yep.
I see. Thank you.
And right, and I think I actually forgot to say here, we have sort of theoretical numbers out of the model, and then our data. I couldn't find an undergraduate to exploit, so I had to do it myself. So we have 10 trees and a few thousand leaves on it, and I'm just counting what these numbers are, and they're pretty close, most of them. So yes.
I see. Thank you very much. So I see that there's a question in the chat. I will read it out loud because it seems that there is a lot of background noise, right? Yeah. So the question is from Bastian Malain, I think. Sorry. So it is regarding topic 1, and
Okay.
the question is: there a characterization of distributions that can be built as distances on metric trees?
That's a good question. And I don't know. I don't know of it. I mean, I think I probably vaguely thought of that when we were doing this a year or so back, and I didn't find any relevant literature. So this would this would certainly be relevant literature. So I don't know. Right. So I don't know. We actually. Right, the second paper I mentioned kind of has gotten beyond actual distances on metric trees because you can do some mixing and spreading out. You can do some other tricks, but it's still sort of based on trees. But yes, this would be interesting to know. And even if our conjecture is true, then you kind of have many other conjectures, which is firstly if I sample three points and look at the three pairwise distances, now certainly the triangle inequality does come into play, and we have no idea how to do that. And also, you could ask if the general conjecture is true, can we do it in infinite dimensional Hilbert space? Yeah, again, it's sort of I think an endless source of problems here.
Okay, good. Thanks a lot. And so let's see if someone still has questions. Yeah, so yeah. Let's just wait a second. In the meantime, let us thank you for this very inspiring talk. And yeah, you reminded that on your website you have these slides, right? And
On my website, I have the slides from last time I gave the talk, which are almost exactly the same. But again, the important thing is that if you can click on the links and it'll
exactly,
do
yeah.
something. Yeah.
Yeah. That's very nice. I think, well, let's see, but probably we will also leave them on the website of the seminar as well. Then they will be also together with Shankar's ones, and so the audience can see them also from there. And so, well, I think we can start thanking you again for this very inspiring talk. And yeah, thanks everyone
Okay.
for being here.
Thanks. It was fun. Fun
Yeah,
to do.
thank you also for waking up early to do.
Okay, you're welcome.
Yes, thank
You're
you.
welcome.